Hello, everybody. My name is Xiaolin from Texas Instruments from Dallas, very close to here. First of all, I want to thank Al and Brian for your invitation to this event. It's very educational for me, and also I get the opportunity to meet a lot of my previous colleagues from Texas Instruments. So, have my picture there. Thank you. So today I'm going to talk about, I need to apologize as well. Don't have any single formula in my presentation. So I'm going to take this opportunity to talk about the Internet of Things, opportunities and challenges, especially from a semiconductor vendor point of view. First of all, we think the IoT is an enabling technology. So what we mean by enabling technology is it enabled many, many applications. I still remember in 1996 when I joined Texas Instruments, my boss at the time told me, don't try to do any research without having a problem. So basically, what he told me is, if there is a problem, then you need to do solving the problem. So with Internet of Things, I think the key is it helped solving a lot of problems that we're facing today. So here I just want to click some example. I wouldn't go through all of them. They're covered wearables, building automation, smart cities, and all these areas. But to summarize them, there are only two key problems we're solving in the Internet of Things. First one is to make our life more convenient, to make our life, personal life or home life more convenient. Second problem we're solving is to make our product efficiency, we call the productivity, much better. So these two are main drivers. One is more from, I think, a consumer, personal perspective. The other is more from industrial, factory perspective to drive the Internet of Things is happening. And I think this morning we spent a lot of time talk about what is the video connected through internet, and also what about 1 million people are connected so far, and our social network, our communication become mobile, and a lot of high quality 4K video is being going to the mobile cell. So this morning we talk a lot about that. But can you imagine, what if there are 50 billion things or components or machines are all connected? So what's the challenge there? What does that mean to us? So to make things more simpler from application to application, I think this morning we have I think Brian gave us a talk about the node and the edge intelligence and then cloud intelligence. I think we're very much echo that vision. So to make things simple, the building blocks of Internet of Things, that's organized them into these three categories. The first one, we call that nodes. Second one, we call gateway or edge intelligence or edge computing, or I think fog by Cisco. There are many different ways. But anyway, there is something in the middle. And then ultimately, there is high performance computing. That is the cloud side. And let's see what's inside these nodes. And in these nodes, we definitely have MCU, and we have processors if we need a little bit more computing power. And we have wired or wireless connectivity, and we have sensing. Because one big thing with Internet of Things is we need to sense the environment to know what's going on in the environment. Plus, there are a lot of analog signal chain. Convert the environmental analog signal into the digital signal so the microprocessor or processor can process. And on top of that, I want to emphasize one thing is the power management. Because, as mentioned, there will be 50 billion components connected in the future, but we're not going to have many network admin available. So how we can make sure the components in the network not running out of battery in 10 years period of time or even longer. So all this together is composed of a lot of things in the node side. And let's take a look at the edge side. In the edge, it's pretty much similar. It has MCU or processor. It has connectivity to both sides. One side to the node, the other side to the cloud. And these could be different kind of connectivity. I think a previous presenter mentioned about from node to edge, it could be something like a low power RF or wired connectivity. But on the other side, it could be cellular or something else. So there are two sides of connectivity in the edge. And besides, always have a lot of analog signal chain. That's the good news for Texas Instruments. And then power management is also important. Even though at the edge we may not need to run in the battery, but still the heat and a lot of issues, we still want to be efficient on the energy consumption. So on the cloud side, and we usually have multi-core, high-performance computing machine, and also analog signal chain, and also power management. So with all these building blocks, if we put them in these three, then the situation makes much clearer. And of course, at the node side, maybe the higher level of integration of all these individual chips, for example, into a single SoC is going to happen, which will be challenges that I'm going to talk about. So to make this whole picture complete, it's not so easy. Even though we simplify that with the node, with the edge, and with the cloud, but we still have a lot of challenges. Here I listed some of the challenge. First of all, sensing. Sensing a complex environment. I think today's afternoon's keynote speaker talked a lot about a complexity of the sensing or detect the numbers in the environment. It's a complex task, and how to make that kind of intelligence happen in the node side, or distributed in the edge side, and then to the cloud side, that you are not clogging the whole network. And second, I want to also emphasize there are so many different kinds of connectivity standards. I participated Internet of Things Global Summit, I think last month. There is a panel about standards. There is the chairperson of the panel read it through, take about 10 minutes to finish all the standards that's related with Internet of Things. So there are so many of them. So how can we minimize or simplify our work when we have to deal with so many different standards? And power is critical. So I will save my time later to talk more about power. Security is a must. We all know the security, and the security varies from device level to the system level, to the end-to-end networking level, and to the application level. So the security requirements distributed among everywhere. And IoT is complex. Of course, our customer tried to make IoT simpler for the end user, but our semiconductor company's customer usually are IoT developers. They're dealing with very complex tasks, many different applications, many different connectivity standards, plus the resource is very limited, plus you have to handle the power. So it's a complex task. And the data analytics in the cloud is important too. And I don't know if you guys remember, in Texas there was a lawsuit, I think for the smart meter, because people think they're paying the smart meter, their electricity bill should go down. But that winter, it was very cold. So the electricity bill actually end up go up a lot. So there is a lawsuit against the utility company about those smart meter. The reason is those smart meter are installed, but there is no analytics is running. They are only installed for the meter reading, so give more accurate meter reading to the utility, but there is no analytics going on to help to minimize the energy consumption in the home. And that's what happened. So the importance of people will see the benefit of smart meter only when you have the intelligence of the data. You read all the data, and then you do the data analytics, and then you make some smart, intelligent decision, then will show the benefit of, true benefit of smart meter. So I just want to take 2 use cases to show the connectivity part or the wireless communication part. First use case, we call that, it's a new IEEE standard, as you know, called 802.15.4G. You can call that a Zigbee, outdoor Zigbee. That is designed for the smart utility network. To, for example, here what I'm showing, doing the automatic meter reading. And if you take a look at this, first of all, it is a very long distance, or sometimes short, sometimes long. And it's a mesh because it's almost impossible to have every meter to connect to the central office, they call data concentrator, through a single hop. So it's and then it has a lot of unexpected multipath because it could be in the metropolitan, it could be in the rural, and distance is a challenge. So this is a very complex situation. Another situation, just like a Google map, go outdoor to indoor. So inside the building, here is showing another example of 2 in the smart building application. So you have one cluster of sensors in this area of the building, which monitor temperature, humidity, and everything. And you can have another cluster in the other side of the building doing the same thing. And it is very, of course, you can argue, say, I can have a subnet here and a subnet here, and then I have a whole IP network. That, I don't know how many network management or administrator need to get involved. So to make things simple, you really need to take all of these nodes as a one flat sensor network. And how to make that happen? Because traditionally, you put a lot of RF node here, multi-hop, and these are the bottleneck. And now, with the technology, what we call a combo mode is a node that can do wireless and the wire. The wire could be Ethernet, it could be power line, it could be anything that goes through this hallway. And then you can connect this whole network just like a flat network. It's all IP-based network. So these 2 are I just use these 2 examples to showcase there is outdoor version, indoor version of how to get things connected. And the connectivity part is getting more and more challenged with 50 billion units to be connected in the future. And so it's important for us to fully understand what is changed. I hope we all go back, ask ourselves, say, because of the Internet of Things, what have changed? Inside what we're doing and outside what we never imagine what's going to happen in the future. So understand the requirement is so important. So I think the previous presenter mentioned some of these. I just want to mention a little. So first of all, you will see much, much larger number of high-value endpoints. So the number of endpoints is not in the same caliber as what we are talking about today, which is more connected people. And these are usually in the fixed location. Some of them could be mobile as well. And they need to run very long deployed life cycle because simply because we cannot afford to have dedicated service provider or utility to monitor all of them, manage all of them all the time, especially for sensor network, for example. And then they are the traffic type. I think the previous presenter mentioned the traffic type. The traffic type is a little bit different from this morning's audio, video, and quality of experience. It is more of what we call command control. This is a small payload data and only go maybe one round trip or even one direction. But sometimes if it's controlled, the deterministic of real-time responsiveness is very important instead of how much data you can shuffle in a short period of time. And also, those networks, we see that it's not going to happen overnight. It's like when we wake up tomorrow morning, all of a sudden there are another billion things are deployed. It doesn't happen that way. So it's deployed based on existing network infrastructure and enhanced from there. So one example, in the building automation, majority of connectivity actually is not wireless today. It's wired. And it's a proprietary wired standard being utilized in the building through a serial line or some different wire. And you're not going to disrupt all of them. So building a new automated building, you are going to enhance on top of existing infrastructure. So it's an incremental deployment. And the ease of deployment, I already mentioned that, how easy. You cannot have a professional or network specialist to be around to deploy so many nodes. It has to be plug and play, and like somebody get it access point from Best Buy and can set it. Has to work like that. And another thing is the node density or the topology of the network really varies. And there is no single topology works for all, because you have to, somewhere it's very sparse, maybe one network only connect 5, 6 nodes. Some is really dense, could be go thousands of nodes. And so it is very important to have adaptive link range and network footprint. And coexistence with other wireless system. So I just already mentioned so many standards, they still have to coexist today. Unfortunately, they're not going to be all moved to a single one. So how to make all of them coexist? And ubiquity and the reliability. I saw this morning's panel talked about, video has some macro block, might be okay, audio is not okay. But for command and control, sometimes, not always, sometimes is even 99% of reliability is not enough. You need to have 100%. And also no battery change for more than 10 years. Again, all these requirements, we put it here, is just based on what we know here. There are new applications we haven't even imagined in the future. So the requirements are keep evolving. So how to handle all these kind of situation? We know no one single connectivity standard will win the IoT world. So already mentioned a lot of there's Wi-Fi, Bluetooth, and power line. There is Prime, G3, P1901.2. There is EtherCAT, 6LoWPAN, Zigbee, you name it. With all these kind of technology, how we be able to build a very robust connectivity for the Internet of Things. One thing I want to mention here is just one example. I think the game is changed. We can no longer work the way it was before. And when I was in a TI for almost 20 years, I think we're really trying to do mostly, it's a hardware company, and we try to do software, but software is product specific. So with Internet of Things, one game change definitely is we need to tie hardware and the software together, what I call a platform game. Why platform game? Because only you invest on the platform, then you can guarantee you're able to meet all the requirements that I mentioned in the previous slide. And the platform game means open system. The system is open, and open system is different from open source. I just want to clarify. Because within the whole system here, I can still have some components that is object code only because I have IP. I cannot put it open source, but the key is all layer by layer. the APIs are very well defined. For example, in the lowest layer, we provide you a radio library. We provide you a sensor library to help you all kinds of sensors. And we provide you power management library. For example, you can utilize it as a tool, and you can build everything on top. Or you can even go up. So you go to the second layer, which is the media access control layer. And the third layer is the adaptation layer. And above is TCP, IP, UDP, and all the IP stack. And also on the top is something we call the IoT agent. The IoT agent will allow you to be able to connect to the cloud instantaneously. And these are all the key components layer by layer. And we provide this platform as a toolbox. Not necessarily will give you a turnkey solution, but give you a toolbox that you can build. You as an IoT developer provide you short time to market. You can do the best, easiest IoT product at the end, but in the shortest period of time. So this is and within these building blocks, we have a lot of ubiquitous, which including time-slotted channel hopping. I'll spend a little bit more time, and coordinated sample listening, and all these unique ideas are targeted for reliability, and the reliability ended with better battery life. So this is an example of what we call time-slotted channel hopping. It is part of 802.15.4 E. E is the enhancement for the sensor network. So if you look at like a regular Zigbee, your radio is either 2.4 or sub 1, you turn it on. But now the radio have divided, the frequency is divided in a lot of sub-channels. And they are hopping around to increase. For example, if you have a Wi-Fi interference at the same time, and then you can jump around, actually be able to get better reliability. With better reliability, you don't do retransmission, so you end up with better battery life. And on the vertical side, it's time-slotted, which means your radio is not always on. Your radio is only on when you do know you need to listen. Because as we all, communication people all know, the power consumption majority is on the listening part, because we don't know when we're going to have a data for us. But with this kind of time-slotted mechanism, synchronization mechanism, you know when to turn on the radio. So with this, plus the semiconductor technology itself, reduce the power consumption per joule, and then you are able to achieve the better power consumption, reliability at the network layer. So here is one system where another technology we believe is not a single connectivity for all. So we think because of Internet of Things, the time for wired and the wireless hybrid solution is come. I already showed the previous example in the building automation and also smart utility network, that with the redundancy of wireless and the wired, put them together can give you 100%, almost 100% connectivity. So you are maybe paying a little bit CapEx to get the much better OpEx, because your node, your 20 billion nodes are unanimously connected very reliably. And this is a system showing we have a dual core that one side can handle power line communication, the other side can handle the wireless, sub 1 gigahertz wireless simultaneously. And you can make it, it's a software-defined radio, and you can make it, it's a software-defined PLC as well. You can make it a dual PLC, or you can make it dual RF. So you name it, with all kinds of flexibility. So here I just want to summarize with what we believe as a semiconductor company. What are the challenges make the IoT happen, and what is needed? Just to summarize, connectivity, one size does not fit all, and we need a broad variety of wired and wireless standards need to be mixed together, and how to enable them. And the power is critical. It's driven by network protocol and as well as silicon. So you cannot just standalone work on silicon but not the network protocol or vice versa. And security is a must, and built-in hardware acceleration will assist the security, even end-to-end security, to happen much easier. And complexity, how to get the complexity addressed is intelligence for simplicity. So the developer's task is more complex, but end users' experience are much better. And rapidly evolving, we have to have a flexible hardware like the one I'm showing, the software-defined dual-core software-defined radio and software-defined PLC, to be able to handle all kinds of different standards, sometimes proprietary, sometimes standard, all be able to handle them without changing any hardware. And IoT success comes from blending software systems and silicon. So at the end, I want to show a clip of a commercial from our customer who is using the software-defined radio solution. And these are.
Innovation is constantly changing the world we live in. It fuels our dreams, drives our progress, and creates our future. And now, Itron is changing the way we think about grid automation and communications. Introducing Itron Riva, a revolutionary set of technologies that create a world of new possibilities for the Openway network. It begins with unprecedented computing power throughout the network, including location-aware grid assets, devices, sensors, and meters communicating and working together. Now, grid sensing, measurement, and control can happen anywhere in the network, giving utilities more meaningful and timely insight to improve and even automate decision-making. With intelligence everywhere, from the edge through the infrastructure to the back office, the possibilities are endless. This includes new applications for revenue assurance, outage management, transformer monitoring, localized demand response and load control, and more. Also, for the first time ever, Itron Riva combines RF and PLC in one communications module, enabling data to flow dynamically, intelligently, at the fastest speed, and along the most reliable path. This new adaptive communications technology assures high-speed, resilient communications for the smart grid, smart metering, smart cities, and whatever the future may bring. And it doesn't matter where you are. This technology works seamlessly with both dense, difficult urban environments and sparse rural areas. Even better, with minimal infrastructure and only one network to operate, it eliminates installation difficulties and reduces cost of ownership. Welcome to a new future, made smarter with Itron Riva and its groundbreaking edge intelligence and adaptive communications technology. And it all comes to you from Itron, the global leader in utility automation. Best of all, this technology is ready to deploy today. Itron Riva, taking the Openway network to a new level and bringing us closer to a more resourceful world.
Thank you.
I have one. How does this relate to, a few years ago, and I'm not in this field, wireless sensor nets?
Actually, a lot of work that is being deployed here are very heavily relying on many, many years of investments from NSF, DARPA, on the sensor network in the academy. It's just in the past, I think, only utilized in the military field, very limited visibility, but with the Internet of Things, it becomes reality. So a lot of things are not happening overnight like that. It's especially the sensor network, the network protocol, there are many coming from academy, and it's becoming into the industrial standard recent years.
I can't see who's, here we go.
Hi, Don. Can you elaborate a little bit more on the built-in security requirement for these sensor nodes?
Yes. Security is always, I I call that a never stop running chasing game, Tom and Jerry game. And so built in the capability, it really divided into device level and the networking level and the application level. And at the device level, for example, we have technologies to protect the memory we call the anti-tamper. So, for example, the firmware, when it's downloaded, then it's protected. If anybody tried to download again without authority, it damaged the whole system. So these are the anti-tamper features that is built inside the CPU, the memory architecture, as well as a lot of logic. And there is another level of security, usually you call that in crypto engine. So you have a lot of hardware accelerated crypto engine. It's keep growing and to be more and more secure. So you can put the data that you're going to put into the network and to be very, very reliable. Another one is what I call the end-to-end security, which is related with provisioning, related with the key management. For example, how to protect the key in the device. That becomes, one is unique and it's difficult to be able to attack. And these are a lot of technology that tied with the uniqueness and the secret of the key management. These are all be able to provided by the semiconductor company. But the one thing I think is which is maybe related with whenever you do security, it's a lot of like export control kind of limitations. So to do that, so maybe you can break down the security into instruction level instead of put the whole algorithm as a hardware accelerator to make it happen.
Hi. Do you believe the 802.11.4G is going to be more common than 802.11ah and Bluetooth Low Energy?
Well, with Raj Talari here, I guess we don't share the same. Yes, I think two of them will coexist. As I said, many standards will coexist, but 802.15.4G we believe is a more mature standard because standard is finalized about 3.5 years ago, and versus 802.11ah is about ready to freeze. So maturity-wise, I would say maybe 802.15.4G. But again, one is leverage the existing Wi-Fi infrastructure. The other is more leverage Zigbee kind of mesh. So each has pros and cons. I guess when you go to specific application, you're going to choose whatever one that fits you the best. The key is you have the flexibility to be able to support the coexistence and support the multiple standards.
Thank you.
Thank you.